Today we'll be doing chemistry A-levels paper 2, which is AS level, and this is October-November 2021. So let's start with the first question. And okay, so the first question says sulfides are, wait a second, sulfides are compounds that contain sulfur but not oxygen. Okay, they've stated that, so we don't need to put much thought into it. Carbon disulfide, which is CS2, is a volatile liquid at room temperature and pressure. Now we need to know what they need to know what is the meaning of volatile. Volatile means so any substance which can be easily evaporated. So if there's a substance over here, let's say it's CS2 in this dish, and it says that it is a volatile liquid at room temperature. So if this liquid CS2 is at room temperature, let's say it's at 25 degrees Celsius, right? Now it will keep evaporating. It will be easily evaporated, and it won't even require much heat. So we just say that the substance which is easily evaporated and turned to gas easily. Okay, that's what you need to write. That's all you need to write. Okay, now for draw a dot and cross diagram of this CS2 molecule. Now we know. Okay, let's open the periodic table. Let me write it. Um, Periodic table. Let me erase that. It's very confusing doing that. Um, okay, so over here, this is carbon. Carbon is 6. Carbon is 6, which means the electronic configuration is 2.4. What about sulfur? Let's look at it. Sulfur is 16, which means sulfur would be 2.8.6. Now, if we draw a carbon over here and two sulfurs at both at the sides of the carbon. Why are we drawing at the sides? Because this carbon is the central metal atom, central non-metal atom, and these sulfurs, they're because they're twice in number, so they each will be bonded with one carbon, with the carbon, one sulfur with on one side of the carbon. Okay. Now we know that the carbon, it has 4 electrons, and the sulfur, it needs 2 electrons each, right? So what we do is we are defining carbon's electrons as dots, okay? But over here I'll be changing the color as well. So it has two electrons over here for the valence shell. So two over here and the rest of the two over here. Okay, which means that the carbon's valence electrons, they're full now. Now coming on to the sulfur ones, so it needs six. It has 6 electrons, right? So 1, 1, 2, 3, 4. 1, 2. Sorry, 3, 4. I'm making a cross. It's not very neat. 5 and 6. Now, if we look at this shell, the sulfur's orbital, we have 1, 2, 3, 4, 5, 6 of 2 of carbon and 7, 8. So we know that this shell is complete. The orbital is complete octet. Now, same goes for the other sulfur. 1, 2, 3, 4, 5 and 6, and 2 of these, so it makes up a complete octet, which is 8 electrons in the valence shell. Now coming on to the carbon, is it complete octet or not? So 1, 2, 3, 4 of its own, so these 4 electrons, and 5, 6 and 7, 8. So these 4 electrons of each sulfur atom. So this is the dot and cross diagram of CH2 molecule. I hope you understood. Now suggest the bond angle of CH2. So over here, if we look at it, it's like this, right? It has no lone pair. The carbon, it has no lone pair of electrons, right? So we know that because they are both bond pairs, they would have equal repulsion from each other, right? So it would form ever linear angle, or we can say 180-degree is the bond angle. So the angle between these two is 180. Okay. Now over here, CH2 is a liquid under room conditions while CO2 is a gas. Okay. Explain what causes the difference in the physical properties of CH2 and CO2. Now it says that CH2 is a liquid under room temperature and CO2 is a gas. Now what's difference between the two? Over here there's a sulfur and over here there's oxygen. So if we look at the electrons, because the atoms are different, let's look at the electrons. So sulfur has 16 electrons and um, sulfur has 16 electrons each, right? So total electrons would be 32. And for oxygen, there are 16 electrons for both oxygen atoms, which means oxygen CO2 has less electrons than that of CH2. So when there are less electrons, the van der Waals forces, they are weaker where there are less electrons, because um, the induced dipole forces between wait, give me a minute. So wait, sorry. Okay, so this is CO2 over here. It also has double bonds with each oxygen. Now these since CO2 has less electrons, which means that how are they uh, how are they gaining the energy to break the bond, right? So this would require less energy. Why? Because it has less number of electrons, so the induced attraction between the molecules between carbon and oxygen, that's less. Why? Because there are less electrons, so it will be easier to break the bonds for these two, the carbon and oxygen bonds. Okay, so we write that um, CS2 has more electrons, has a double the number of electrons, which means more, which means there is more energy between the molecules. Sorry, wait a minute. I guess it's stuck. I'm not sure how to deal with it. Okay, so what we write is CH2, let me erase this. CH2 has more electrons, that's what we write. CH2 has more electrons, and it requires more energy to overcome the attraction between between the molecules of CH2, and they have CH2 has stronger induced dipole attraction. Stronger induced dipole attraction between molecules. Okay, that's what you need to write. That's the keyword over here. Okay, now moving on to the enthalpy change of combustion of CS2 is represented by the following equation. Okay, now define the enthalpy change of combustion. So when 1 mole of, what do we say, when 1 mole of CS2 over here, which is when 1 mole of a compound, which is CS2 in in this case, so we write CS2 is burned in excess of oxygen to produce carbon dioxide and H2O, which is water. Okay, that's what you need to write for this definition. The table shows the enthalpy changes of formation of CH2, CO2 and SO2. Okay, use the data in the table to calculate the enthalpy change of combustion. Okay, we need, okay, wait, this is the equation of combustion of CH2. So we need to find, basically we need to find this thing over here. Now if we look at it, we are given with the enthalpy changes of formation. So we are given of the formation of this CH2, CO2 and SO2. Okay, now if I write the elements over here, carbon plus sulfur, um, and oxygen, and that's it. Okay, so over here, this carbon and sulfur, they are reacting to produce CH2, and that's how CH2 is formed. So what's the formation, what's the enthalpy change of formation? That's plus 89.7. But there's one slight difference, that we need to write 2 over here. Now O2, if we just write 3 over here, that's the same thing, right? So nothing's changing in oxygen, so we don't mention the enthalpy change of that. Now for CO2 again, let's put an arrow from here to here. Carbon is 1 and oxygen is 2 over here. Okay, so for when this is formed, the enthalpy change is minus 394. Let's write that, and let's move on to this again. Now SO2, 2 sulfur and 3 and 4 oxygens. So the product side, it also has 1 carbon, 2 sulfur and 6 oxygens, right? So they need to be balanced. Now what do we do? Because it says 2 moles of SO2, so we multiply it. Because this is the enthalpy change of formation, if you look at if you look over here, it says per mole. So when there are 2 moles, what do? We multiply the number with 2. So 2 multiplied by minus 297. Now if you so these are the formations, the arrows, these are the elements or the atoms, and we use the formation. So carbon plus sulfur, it forms CH2, carbon plus oxygen, it forms CO2, and sulfur plus oxygen, it forms sulfur dioxide. Now what do? These are the formations, and it is allowing us to move to this path indirectly or this path directly. Now there are two paths, right? So we can add so wait we can add these two paths, and they will be equal to these paths, the sum of it. So plus 89.7, this plus 89.7, let me write it, plus 89.7 plus this, which is the combustion. We need to calculate the combustion, right? So we write x because we don't know what that is, and which is equal to minus 394 and plus 2 multiplied by minus 297. And when you solve this, you can calculate the value of x. You will add these two numbers and then bring this 89.7 to the other side with a negative sign, and you can calculate the x like that. Now why do we do that? Because this path is equal to this path, right? The wait the starting point of both reactions are the same, and the ending point is also the same. So it starts from carbon and 2 sulfur and 3 oxygen gas molecules, and it ends at carbon dioxide and 2 sulfur dioxide. And over here it also both of them, the ending point and the starting point is the same. So we can equate the two because the answers would be the same. That's the Hess law, and that's how you calculate the enthalpy change. Now, moving on to the next part, it says hydrogen sulfide gas is slightly soluble in water. It acts as a weak acid in aqueous solution. State the meaning of weak acid. Now, what does a weak acid mean? It means that it partially ionizes in water. That's all you need to write. Okay? Give the formula of the conjugate base of H2S. Okay. Now, if we look at it, let's see. So, hydrogen sulfide is slightly soluble in water. Okay. So, H2S, when it ionizes, what do we get? We get one H positive ion, of course, and whatever is left. So, we are left with H and S minus ion, plus H minus ion. Now we know that this is the acid, right? So we know that the other one would be the conjugate base. So this HS minus, that's the conjugate base. H2S reacts slowly with oxygen dissolved in water. The reaction is represented by the following equation. Okay. Explain with reference to oxidation numbers why this reaction is a redox reaction. Okay, what is a redox reaction? When oxidation and reduction both are occurring in the same reaction. Okay, let's see. Whenever hydrogen is bonded covalently, it will always have a charge of +1, and we can find out the charge on sulfur, which would be -2. Why? Because if we look at it, so H2S, right? This is a neutral compound. It has a 0 charge on the whole compound, right? And we know this is +1. So when we multiply this 2 with +1, we get +2, right? So plus 2 plus, we don't know what sulfur's oxidation state, so we just write plus x and we equate it to 0. So automatically what would be the answer for x? It would be minus 2. So we know that the charge on sulfur, it's minus 2, right? Now when we move on to the oxygen, because it's existing independently, it's not bonded with anything, so it's just bonded with another oxygen, not a different atom. So it would be 0 over here. Let's move on to other one. Over here we always know that oxygen is minus 2 over here, and it's plus 1 over here as well. What about over here, sulfur? Because it's existing independently, it's not bonded with anything, so just like this one, this would also be 0. Now they need to know if both oxidation and reduction are occurring in the same equation. Let's see. Hydrogen, the oxidation state is remaining the same, the oxidation number is the same. From sulfur, from minus 2 to 0, which means that it's losing electrons or gaining electrons. What is it doing? So it's losing 2 electrons, and that's why it's moving to the positive side. Now over here it's becoming 0 to minus 2, which means it is gaining electrons. Now the loss of electrons, that's oxidation, and the gain of electrons, that's reduction. So we know that both of the reactions are occurring, so it is a redox reaction. That's what we need to write as well. Okay. The compound As2S3 is the common mineral. It is heated strongly and it forms a mixture of products. A sample containing 0.198 A2As2S3 is placed in 0.1 dm cube of pure oxygen in a reaction chamber connected to a gas syringe at room temperature. These reactants are heated until no further change is observed. The products are then cooled to room temperature. Calculate the volume in dm cube of present at the gas present at the end of the experiment. So what do we need to find the volume of? We need to find the volume of the gas present at the end of the experiment, of this one and which one? Maybe some of some of the oxygen, it did not react fully, so maybe this or maybe not. We'll have to see about that. Okay, now over here, uh, let's see how many marks. Okay, so it's 4 marks, which means it's a lengthy process. Sorry, over here. Okay, now let's read the question again. A2S3 is As2S3 is heated strongly in air. Okay, so it's reacting with oxygen and forming As4O6 and 6SO2. Okay, that's perfect. Now we know what the mass of As2S3 is, and we know what volume of oxygen is used, which is an excess, which we know, from which we can figure out that some of the oxygen will be left in the remaining gas, because we need to know the remaining gas, all gases, mixture of gases. Okay, so if we write over here, give me a minute. Okay, so if we know what's the mass, it's 0.198, 0.19, sorry, 0.198, right? Now we can calculate the moles of this after we have calculated the MR of As2S3, right? So if we do that, let's see, moles is equal to mass divided by MR. Now what's the MR of As2S3? Let's see from the periodic table. As2 is, let's calculate. Where is As? Yeah, over here it's arsenic, right? So it's 74 Well, let's say it's 75 into 2, As2 and S3, which is sulfur. And sulfur we know it's 32. So 32 multiplied by 3, right? What do we get? We get 246. I used my calculator, I did not do the working on the screen. So we know what the mass is, so let's write over here. Moles is equal to 0.198 divided by 246. Okay, and the answer would be, let me calculate that as well, 0.198 divided by 246. That is 0.000805. Sorry. Let's keep it like that for now because it does not get confusing for you. Now, that's the, what is it? That's the mole. Oh, sorry. I can't move it. Okay, sorry. Yeah. So that's the mole in the experiment, right? Now, what is the mole of uh, sulfur? What is the mole of sulfur dioxide which has been formed? So in the equation, what's the ratio of the gases? Sorry, what's the ratio of the two compounds, As2 and As2S3 and 6SO2? It's 2:6 of the moles, right? And in the experiment, what are the moles there of As2S3? They are 0.000805, and we need to calculate the moles of SO2. So we cross multiply. What do we get? We get 2x multiplied by 6 multiplied by this number over here. So when we do that, we get multiplied by 6 and divided by 2. We get 0.00241. Okay, that's the answer for moles of SO2. Now, if we need to calculate the volume, what would we do? We will use volume, moles is equal to volume over 24. We'll use 24 when the volume we need is in dm cube and we need the answer in dm cube. So moles are 0.0241. We multiply this number with 24 and we'll get the volume, because when we multiply this from here we'll get 24. So the answer would be, let me write it down. So it would be 0.05795 dm cube of SO2. That's the answer for SO2. Now, what about oxygen? What do we do about that? Let's see. So, 2 moles are reacting with 9 O2, right? Let's do that again. We know the moles of As2S3, which is 0.00805. Let's do the ratio again for As2S3 and oxygen. The ratio which is given in the equation is 2:9, and we know the moles for As2S3, which will be inserted over here with the ratio we need to find out, which means, what does it mean? What do we need to find out? We need to find out how many moles are reacting when this much mole of As2S3 are reacting, how many moles of oxygen are being needed, right, are being consumed. So 2x is equal to 9 multiplied by this number. Now what is this X? The number of moles which are being used in the reaction. So if I calculate it, 9 multiplied by 0.000805 and divided by 2, I get, let's write it over here, I get 0.00362. That's the mole of oxygen used. Now if I need to calculate the volume of oxygen used, what do? We multiply this 0.000362 with 24 to calculate the volume over here. So when I multiply it with 24, I get 0.08694. That's the dm cube of O2 used. Now over here we need to find the volume which is present at the end of the experiment, right? Now this is the one which is used, and this is the number of this is the volume which was given in the start. So when we subtract this, we'll get the volume which has not reacted, right? So when I subtract 0.0694 from 0.1, we'll get that value which is 0.01306 moles, dm cube left at the end of the experiment. Okay, and this value right over here, this is also the one, this is the one which this is the value of the volume of SO2 produced. So when we add these two, we'll get the complete volume which is present at the end of the experiment. So 0.05795 added with 0.01306, we get 0.071. Let me erase this. So we get, the answer is over here 0.071 dm cube, and that's the answer. I hope you understood the question, and let's move on. State the environmental consequences of releasing SO2 in the atmosphere. So we know that when it combines with water, it forms H2SO4, which results in acid rain, and it is not very it's very harmful to our health and other buildings and aquatic animals. Now SO2 can be removed from the air by reacting it with NaOH. Construct an equation for SO2 with NaOH. Include state symbols. Now we are given with the state symbols of these two, so we don't need to worry about that. So let's write it. SO2 plus NaOH, which gives us what do we need to do? We need to remove SO2. Okay, how are we going to do that? So if I combine, so give me a minute. So when they two react, so one is an acidic gas, and one is a base. So when they react, it should form something like sodium silicate and water, because water, we know that whenever acid and bases react, we get the water. So we can write water first, H2O, and sorry, I wrote 0, and whatever is left, we're going to combine in another reaction. So Na is left, sulfur is left, and oxygen is also left, right? So, but there are only two oxygens, but we know that there's a compound which for which the formula is sodium Na2 and SO3. That's sodium sulfite. Silicate is with silicon. Sorry, I confused the two. Okay, now we know that this. Okay, let's balance it. Um, sulfur over here and sulfur over here. Sodium, there are two sodiums, so we write a 2 over here. And coming on to oxygen, so two oxygen over here and one oxygen over here. So two oxygens and two oxygens, four oxygens, and three and four oxygens over here, and two hydrogens over here, and two hydrogens over here. Now it is balanced, and this is gas. NaOH is aqueous. H2O is liquid as we all know, and sodium sulfide, that is sodium uh, that's sodium sulfide. So sodium sulfide is aqueous because it is dissolved in water. This water, so we say that it is a compound which is dissolved in water, and the uh, state symbol would be aqueous, which is AQ. We write it as AQ. Okay, that's question number one. We are done with question number one. Let's complete the second question in the next class, and similarly in the next lessons we'll be doing the other questions as well. Hope you enjoyed the lesson and you understood everything, and if you have any questions, do let me know in the comment section, and stay tuned for the upcoming lectures. See you soon.